This week we will talk about a bit of cardinality. Actually, not just a bit. We'll talk about mostly cardinality. Specifically, we'll talk about countable, uncountable, and then we'll move on to power sets. After that, we'll talk a little bit of divisibility. First of all, we have countable and uncountable. Here is the definition. A set that has the same cardinality as natural number is called a countable set. Okay? If you look at this definition, you'll see that finite sets are not countable. Finite sets are not countable. This may be counterintuitive because you'll think, oh, if it's finite, we can count them. But based on the 102 definition, because countable set has the same cardinality with natural number, and we all know that finite sets and natural number, they don't have the same cardinality. So in this course, finite sets are not countable. But in other places, let's say generally speaking in math environment, we all consider finite sets as countable. So we have two words for different countability. For the sets that have the same cardinality with natural number, we call them infinitely countable, and finite sets we just say they are finite. So is 1, 2, 3 not a countable set, right? We just say 1, 2, 3. So your example, I'll write it down. Your example, you said that's A equals to 1, 2, 3. We just say A is finite. We don't say it's countable. Does that make sense? So in 102, when we talk about countable sets, it has to be infinite. So it has to be infinite and it has the same cardinality with natural number. So something like this, we call them finite. They are not countable. Okay, so since we have countable set, we also have uncountable set. And the definition is the following. An infinite set that is not countable is called an uncountable set. So just by looking at the definition, there is something I need to remind you. We know that, just by looking at the definition, you should know that if A and B are both countable, then they have the same cardinality. Okay? Why? Because they both have the same cardinality with natural number. But this statement is not true if we change the countable to uncountable. Okay? This is not true if A and B are uncountable, then you don't know if they have the same cardinality. Why is that? Because for uncountable sets, you might have, for example, a set that has the same cardinality with real number. You might have a set that has the same cardinality with a power set of real number. And you know that by Cantor's theorem, which we'll talk about later, the power set and the set itself, they have different cardinality. So for uncountable sets, we actually have different cardinality. So if you have two uncountable sets, you don't know if they have the same cardinality. Okay, so this statement is not true if you change countable here to uncountable. Any questions so far? Okay, seems like we don't have any question. Let's look at the first theory. The first theory is that the set of natural numbers m and the set of rational numbers have the same cardinality. So what does this theory tell us? Anyone know? Q is countable, exactly. So this is telling us Q is countable. The proof of this theory is in your textbook. The proof is really, really important, so please make sure you understand it, because you can use a similar technique on some other proofs. Okay? Theory 5.4.3, it says that the set of real numbers R is uncountable. And you all remember how did we prove this? From the textbook, how did we prove this? Exactly. So the proof is called Cantor's diagonal argument. We don't have time to talk about this, but I really like the proof. I can't say if it's important or not. The last word. Argument. You can say Cantor's diagonal argument, proof, theorem. Doesn't really matter. Oh, okay. Anyway, Cantor. I kind of want to talk about Cantor. This mathematician. He's one of my favorite mathematician. For some reasons, when I was taking 102, this proof actually got me. I actually had this wow moment when I saw the proof of this Cantor's diagonal argument. Cantor, this mathematician, when he was discovering this whole infinite things, nobody believed him because, well, everyone think, oh, why do you have different infinity? It sounds wrong. It just sounds wrong. He was suffering from a lot of mental problems, and he was on a lot of drugs. So this is what we joke about when we were just saying that, oh, you can't come up with this if you are not on so much drugs. But that's just a joke. I'm not saying you should take drugs when you do math. Anyway, when he discovered this, he sent his papers to a few famous mathematicians, but nobody believed him. They just threw his paper out, and it wasn't being accepted. This whole concept of infinity wasn't being accepted until another mathematician found the same thing. So you see, sometimes being accepted by the whole math world is not that easy, and we always say, oh, sometimes you need to take some drugs to do well in math. But again, I'm not saying you should take drugs, and it's just a joke. Anyway, I really like this mathematician, and I think his work amazed me. And you should understand this proof, okay? Cantor's diagonal argument. You should understand the proof. I can't say it's important, but it was tested before. Rarely, but I saw once at least. Drugs aren't needed, just getting a little drunk is enough. I think what I said it might be inappropriate, but yeah. Again, I'm not saying you should take drugs, okay? Just to clarify, I'm not saying you should take drugs. And I'm not saying you should drink, although I drink a lot, but I'm not saying you should drink. I guess you guys are still underage. Anyway, let's look at the first activity. Consider the following sets. So we have those 5 sets. The first one asks you to identify the infinite sets. So which of the following, let's give them a number. Let's say this is A. Let's just say this is 1, 2, 3, 4, 5. Which of the following are infinite sets? Anyone? You can type your answer in the chat and we'll take them up. Let's... No, don't guess. Don't guess. Why are you guessing? Don't guess. Actually try it. No, not all of them. Okay, let's look at the first one. The first one, x in rational number, such as x squared is in natural number. Is there any other way to write this? Anyone? Do you recognize what it is? Such that x squared is a natural number. So let's write this down. X squared equals to 1. So what's x? X is 1 or negative 1. X squared equals to 2. What's x? Wait, can be this, can be 2, because this is a rational number. Sorry. So the next one will be 4. What's x? Plus or minus 2. And then x squared equals to 9. And we have plus or minus 3. Okay, so continue. What is my set? Why is 2 that in there? Because if x squared equals to 2, your x is not a rational number. Not really perfect squares. And not really integer. You guys are close, but no. Something, yes, you're right, we're talking about integers. Because you see, we have plus minus 1, plus minus 2, plus minus 3. But that's not all the integers, right? Yes, all integers except 0. So this is all integers. All integers except 0. So is this infinite or not? Why is it not infinite? It is an infinite set, okay? So we have 1. Number 2, it's a power set of negative 1, 1. Negative 1, 1 is an interval which includes all the number between negative 1 and 1. So this itself is infinite already. So the power set of this, the cardinality is going to be even bigger than the cardinality of this. So number 2 is infinite as well. Number 3, the Cartesian product of n and n. Well, natural number, we know it's infinite. This is infinite as well. So the whole thing will be infinite as well. So 1, 2, 3. Number 4, anyone know what's number 4? What's the other way to write number 4? 3, okay, 3. This is infinite, right? Do you agree? natural number is infinite set. So infinite set, Cartesian product, another infinite set will give you infinite set as well. Because Cartesian product is like you take an element from one set and take the element from other set, so it's like pairs of numbers from natural numbers. So that's gonna be infinite pairs of numbers as well. Okay. Number 4, someone said real numbers without positive integers. Okay, exactly. So is this infinite or not? Number 4? Yep, okay. What about number 5? What's number 5? Any other way to write it? Okay. Someone said -1, 2. No. Number 4 is infinite, yes. Number 5, what's number 5? -1, 0, 1, 2, exactly. Okay, so number 5 is finite. Alright, 2, identify the infinite countable set. Well, we know those are infinite. Which of the following are countable? Countable? 1, 3. Okay, exactly. Okay, 1, 3. This one should be simple to prove. Okay, it's just integers except 0. Anyone can come up with a function to show that it's countable. Let's prove this one, because the second one would take some time. Anyone? Is P just power set? Yes. How do we prove 1 is countable? That's my question. Yes, you show that it has the same cardinality with the natural number. Yes, so I'm just asking for the bijection. What's my bijection from, oh, oops. What's my bijection from what's it? From natural to the first set. Anyone? You can use a piecewise function. So let me think. So we can have f, oops, map from natural to this. Such as, let's say our f of x equals to Cantor's theorem. Most of the time they don't allow you to use that. Equals to x over 2 if x is even. Let's see, that's gonna give us 1. So for, oh, I need negative numbers as well. So x is even, so 2 divided by 2 is 1, 4 divided by 2 is 2, so 1, 2, 3, 4. So this gives us all the all the positive numbers. And I need another function to give me all the negative numbers. Anyone has an idea? Let's say negative x plus 1 over 2. Would that work? So 1 plus 1 is 2 over 2 is 1. 3 plus 1 is 4 over 2 is 2. So negative 1, negative 2, negative 3. Yeah. So this will give us all the negative numbers. Yep. So this is a bijection map from natural number to this. Okay. How do I prove this? Anyone know? I'm not gonna prove it, but I'll tell you how does it work. Anyone know what method do we use to prove this? It's something I mentioned before. Okay, so to prove this, you need to mimic the proof of this theory. It's really similar, okay? I don't have time to do it because it's gonna take a long time, but it's really similar to this proof. That's why I said please make sure you go home and read the proof, okay? Any questions so far? Question? What 1 means? Oh, 1 is just all the integers except for 0. So x squared equals to natural number, and x has to be a rational number. So when it's natural number, it equals to 1, 2, 3, 4. When a equals to 1, your x is 1 or negative 1. It cannot be 2 because when a equals to 2, your x is not a rational number anymore. So the next one it can equal to is 4. Okay, so when x equals to 4, you get x equals to plus or minus 2. And the next one is 9 because from 5 to 8, your x is not a rational number. So you get plus or minus 3 and so on. You can never reach 0 because x squared is a natural number. 0 is not a natural number. So the result is just all the integers except 0. Any other question? Is implies no. This means x is an element of rational number such that x squared is a natural number. Okay, so you have to satisfy both conditions. First, it's always a rational number. Then x squared has to be a natural number. Proof for 3. Oh, that's gonna take a long time. I did prove it though in one of the videos, so you check that. I did prove it in one of the video. Let me find the video. I'll send the link here. Just give me a moment. But right now, we don't have time to do that. Would the even negative numbers get covered by f of x? Yes. So for example, when x equals to 3, you have negative 3 plus 1 over 2, which is negative 2. Any other question? Okay, I found the video. This video I just sent, somewhere in the video I proved somewhere in the video I proved the Cartesian product of two countable sets is also countable. So that's the same as this, except it's even more complicated. Anyway, power set. Power set, the definition is just that if we have a set X, the power set of X is just the set of all the subset of X. So for example, let me give you a short example. We have A equals to 1, 2. Then what's P of A? It's a set of all the subset of A. So subset of A, we have 1, we have 2, we have 1, 2, and we have the empty set. Okay, so power set of A is going to be the set includes all the empty set of A. No, not empty set, the subset of A. One thing you should know is that if X is finite and the cardinality of X equals to M, then the cardinality of the power set of X is what? Anyone know? Anyone know this? 2 to the power of n, exactly. Okay, this is what you should know as well. Okay, you can prove this by induction. This proof by induction. You can try to prove it yourself. Okay, I think the proof is in the course notes as well. So anyway, let's look at activity 2. Consider set A equals to this. Fill with subset or an element of as appropriate. So I'll give you some time to do those 4 questions. And you can ask me any question if you have. Okay, what's the answer for A? Anyone? What's the answer for A? Both? Yes, both. Okay, both. Could be this or this. Both works. Why? Well, this is the empty set. We know that empty set is a subset of any set. So that's why we can put this here. Also, since empty set is also right here, is an element of A, so the empty set is also an element of A. So it could be both. Yes. Part B. What's part B? Element or a subset? Element, yes, yes. Part B is element. Okay, why? Because, well, it's right here. Okay, the set that has 3 in there, the set of 3, is an element of A. Alright, so this is element. Part C. It's not a subset. The subset will be this. The set of 3. This will be a subset of A. Okay? Part C? Anyone? Part C? Congruent? No. Part C. Neither. Neither is correct. Okay? Well, 4 is not an element. You see, the element of A is the empty set, the set of 3, natural number, 1, and the set of 2, 4. So 4 is not an element of A. It's also not a subset of A because there is no set that has 4 as like, yeah. So it's neither. It's not a subset, it's not an element. Part D, is it subset or element? Subset, exactly. Okay, because 1 is an element of A, so the set of 1 is a subset of A. Okay? Part 2, is this true or false? Number A, the natural number is an element of the power set of A. True or false? Natural number is an element of the power set of A. Think about what's a power set of A, okay? One of you said true. Never mind. False? Okay, it is false. How do I change it so that it's true? Anyone know? So what is an element of power set of A? Exactly, okay? It's a set that has the set of natural number in there. This will be an element of power set of A. Part B, yes. Part B is this true or false? 2, 4 is a subset of A. False, okay? False. So what's the correct one? Element of, exactly. Okay? 2, 4 is an element of A. Part C, the set of 1 and 2, the set of 1 and the set of 2, 4, this whole set is a subset of A. True or false? True, okay? True, this is true. What about power set of A? What do we put here if I write power set of A here? Anyone know? No, I'm not asking true or false anymore. Yes, element, exactly. Okay, so what I want to say is that If a set is a subset of A, then the same set becomes an element of the power set of A. Okay, by the definition of power set, by this. Again, I'll repeat that again. If a set is a subset of A, then it's an element of the power set of A. Okay, it's really important because we need to use that for the next activity. True or false? Prove or give a counterexample. For any sets A, B, the power set of A intercept B equals to the power set of A intercept the power set of B. I'll give you some time to think about it, and we'll take it up. Just to save time, I'll tell you it is true. So just try to prove it. So this is a time to refresh your memory about how to prove two sets are equal. What do we need to do? Think about that, okay? And just use the definition, basically. Let X, yes, you start with the correct one. Okay, now, are you guys done? Okay, we have 5 more minutes left, so let's look at this. Basically, as one of you said, our first step is let X be an element of what we need to prove here. Okay, so let X be an element of the power set of A intercept B. Remember, I said if a set is an element of the power set of a set, then it becomes a subset of the original set, just like here, okay? I just mentioned that. So by definition of power set, X becomes a subset of A-intercept B. This means that X is a subset of A and X is a subset of B. Well, as we mentioned before, since X is a subset of A, that means X is an element of the power set of A. And similarly, since X is a subset of B, it becomes an element of the power set of B by definition of power set. And now you can just add them together. You'll get X is an element of power set of A intercept power set of B. So this shows that this is a subset of this, and the other way around is just going backwards. Okay, so this shows that they are equal. Any question? Yes, I used if and only if. That's why I didn't write it twice. I didn't show. Well, I showed. Yeah, it's biconditional, so it's okay. Any question regarding this? Question? So the key of this question is just understand the definition of power set. Okay, so remember the definition. Okay, the power set of X is just a set of the subset of X. Okay, so if A is a subset of X, then A becomes an element of power set of X. So we just use definition for each of the steps. Any question? Can I move on? Okay, seems like no one has any question. So if no question, I want to talk about Cantor's theorem, which I actually mentioned already. Cantor's theorem is just saying that the set X and its power set, they don't have the same cardinality. In fact, the cardinality of the power set of X is strictly greater than the cardinality of X. Okay. So some common countable sets. This is just like a summary. So common countable sets, we have natural number, rational number, integer, even numbers, odd numbers, countable union of countable sets. This is a good one. Cartesian product of countable sets. This is another good one. Make sure you know how to prove all of them. Okay? Make sure you know how to prove all of them. Now, one thing I want to emphasize is that finite sets are not countable in MAT102. I mentioned this when we talk about the definition of countable sets at the very beginning. So this is not just another reminder. Some common uncountable sets, we have real number, which is proved in class already. Irrational number, make sure you know how to prove this. Intervals, again, make sure you know how to prove this as well. Unions of uncountable sets, Cartesian product of uncountable sets, power set of countable sets, power set of uncountable sets, and so on. Make sure you know how to prove all of them, okay? So it's a good practice. I do the summary because if you see, it's gonna give you, if they ask you if it's countable or uncountable, you can have like a quick idea if they are countable or uncountable. But for the proof, make sure you know how to prove all of them. Divisibility is our last topic. This is just high school material, to be honest. The only thing you might not know is a notation. This means B divides A. B divides A. Okay? B divides A. Or A is divisible by B. If there is any blah 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 blah. Anyway, so this activity, we don't have time to do it, but I proved in one of the video already. I'll send you the link. Last activity, we don't have time to do it, but I proved it before already. So I'll send you the link, and that's the end of the tutorial. Just give me a moment. Let me find it. Oh, there we go. It's around 17 minutes. So this video, starting from 17 minutes, it's a proof of this activity. Okay? And that's it. Daria has some extra practice questions. You can check Quarkus if you wanna practice. Those are pretty good questions. So try them. Extra practice activities. If you don't know where to find them, I'll show you. So you go to modules, click tutorial worksheets and solutions for extra practice questions. Oh, she haven't posted them yet. I will post them. It's okay, I'll post them. So check tutorial week 10, and there are a few extra practice activities that you can do. Actually, I'll send it here. Just give me a moment. I don't know why it's not sending. Oh, there we go. Okay, so there are 3 extra practice you can do, and that's the end of the tutorial. If you don't have question, you can leave now. Bye everyone. Is A a true false value or actual number? Actual number. Actual number. For any natural numbers A, B, C. See? Bye. The notation means A divides B, or B is divisible by A. Just right here. Right here. Oops. Right here. Means B divides A, or A is divisible by B. Okay, I think that's it. I'm gonna stop the recording.